Alright, good afternoon everyone. Welcome to our second lecture of week 7, 12th lecture in the course. Where are we? Well, as I'm sure you heard yesterday, Premier announced that we have more lockdown. The result for us and UNSW is we're not going to be able to get back face to face for the rest of this term. So all your remaining COMP1511 tutes and labs will be online. We'd prefer to be face to face, but as I said, I guess the silver lining is we're better equipped than most courses to do everything online. Huge thank you to all the tutors who've been helping out. Help sessions, there were so many people in help sessions with the assignment and also with the forum, tutors queuing up to work on the forum overnight. So thank you for that. And let me repeat what I said in the last lecture, is this tremendous amount of information coming out about COVID. So you're smart, technically savvy, you can read through all that information and scan it, so make sure all your friends and relatives know about contact locations and all the things they're supposed to be doing and not supposed to be doing. You take advantage of being so smart. And so easy to be able to cope with being online. Alright, and please stay safe yourself. What else is happening? Alright, assignment 1 is in. Assignment 2 is not yet out. Tutors are beavering away, putting the polishing, doing the last touches to assignment 2. All going well. We'll have it out Sunday. If there's thing or two that needs to be fixed up, it might be Monday or Tuesday, but assignment 2 out very soon. Weekly tests are rolling along as usual. Our last weekly test is due in, the week 5 weekly test from before flexibility week is due in 9 AM tomorrow. Another weekly test will roll out. I'm not sure exactly when we'll have it out, but it'll certainly be out by tomorrow evening for you to work on tomorrow evening if you want. This week, the next upcoming weekly test is sort of similar to some of this week's lab exercises. So you might do this week's lab exercises and then this week's weekly test. I think that's the sensible ordering there. Alright, weekly tests. Oh, exam. Yes, we do have an exam in this course. Yes, it is approaching. We have a tentative exam date, so I think it's been sent to students. I think your provisional exam timetable is now visible in my UNSW. We have an exam on the Wednesday of the first week of the exam period. Provisionally, that is. So a big course like this, they're very unlikely to move the date. It'll be that afternoon. Alright, please don't panic at this stage. We usually get well, not quite a flood, but quite a few students contacting us saying, oh, I've got an exam clash, I've got another exam that day or that afternoon, or I've got exam conditions or things like this. Alright, so we know about both these things. We know about all the exam clashes, and we'll email the people who have, we know what courses you're doing, when they have exams, and we'll email the people who have clashing exams saying this is the arrangement, but we won't do that until closer to the date. There are various things that might change still, that it's much better done a week or so before the exam. So at least a week before the exam we'll contact you and say, oh look, you've got a maths exam that day, we're going to do this. So don't contact us yet about that. If you haven't heard anything a week before the exam, yeah sure, get on the course forum and say what's happening, how do I do this, but not now. Some students, equity and what do they call them? The Equitable Learning Services gives some students, a small number of students, special exam conditions. We also know about those, and we'll contact you again by about a week before the exam to tell you how that's going to work. And again, if we haven't contacted you by then, you can get in touch with us, but not now, please, not now. So that's the exam. The nature of the exam we'll discuss in great detail in a week 10 lecture. So again, don't ask how the exam's going to work now. Save it, keep it for a surprise. You've got other things to focus on. We've got this week's lab exercises, which are sort of fun and huge and playing with text and quite clever, so that's nice. And then we get into really deep concepts in next week's lab exercises, crucial concepts in next week's lab exercises. So you've got lots of lab exercises to keep you busy. So much, it's a lot of work in lab exercises this week and next week, plus the assignment to look forward to coming out very soon. And again, yes, you're locked down, but frankly, with the amount of work you've got to do at this stage in a university term, you probably won't able to do much else anyway. So I guess there's that. All right. Let's on screen. I've been coding. I've written a program which seems to compile, and I'm not sure. I can't remember. We should looked at this program before. It's a favorite program of me. It's one of my favorite games. It's Snap. You might have played Snap. It's a very old game, played with cards, and you go snap if two cards the same are put down one after the other, and the object is to be the first person to go snap. And it's played in various ways, some of which, when played as a 6-year-old, involve some amounts of violence, which we don't condone. All right, so I enter numbers 3, 4, 5, 6, and if I hit another 6, my program prints. Oh no, I haven't recompiled this then. Let me try recompiling this. I altered the code so it didn't exit. Come on. There we go, it's compiled. So let's try that again. 3, 4, 5, 6, and then 6 repeated. Snap. So that's the program on the left. Let's pause to look at this program. It's a nice piece of code, actually. It's a lovely piece of code, which should, at this stage, I'm hoping this is looking less scary. Only a couple of weeks ago, this would have looked really intimidating. I'm hoping this code looks less scary. It's got quite a complicated while loop there. It's a weird while loop condition, isn't it? It's a complicated and powerful, but I think you can understand that now. That says while scanf returns 1. What does scanf return? The number of things it manages to read. We're only asking it to read one thing, so it's either going to return 1 or I think 0. I can actually return 0 or -1 to say it failed, but that doesn't worry us. We're only asking to read one thing, so if it's successful, it must return 1. So that says while scanf can read a number, execute this loop. And the loop says if the number read is the same as the previous number, print snap. That's not that hard. Make previous number previous n hold the current number, and then print. Oh, that's a bit weird again, isn't it? Print out the message. Could you make this better? Yeah, it's a little weird printing the message. I told you, what do programmers hate? What do programmers hate? Seeing the same code twice. It's just not good. Could you make this code so it only has one printf? There are bad, well, not so good ways to do it, where you can mangle this loop to not do that. But there is a good way. The good way would be a function, and I'll leave that as an exercise. You can move the printf and the scanf off into a separate function and make that code better. I'll leave that as an exercise. Right. Other thing is, can you spot any weaknesses in my code? I've got a basic problem here. Is what do I initialize previous number to? What I wanted to initialize it to is something so this code can never go snap right there. So I never want to snap right there. So what have I done? I've picked an incredibly unlikely number, which no one will ever think of, to put there. But if they do think of it, my scheme can fall apart. I interrupted it anyway. So let's try it. If the user actually types in 1, 2, 3, 4, 5, 6, 7, 8, 9, it prints out snap straight away. Is there something you can put there that the user can't type? And I think the answer is no. There's no value you can put there such that the user can't enter them. What do you do about that? Yeah, I'll leave that as an exercise as well. How do you get away from this sort of, I'd call that a hack, that doesn't work that well, picking an unlikely but not impossible value? Can you refactor the code, change the code to avoid that? Also left as an exercise for you. It's a tiny program, but there are so many interesting consequences and ways to structure it. Alright, that's snap. So I wanted to do a slightly different version of this, and it's broken. It won't even compile. So what have I tried to do? I've tried to do something involving lines. I'd like to do the same thing as the previous program did with integers, with lines of characters. So look, I've changed it. I've got 2 char arrays. Made them huge, haven't they? A whole 4,000 characters. Is that huge? How much memory on my computer? Oh, I've got 128 gigabytes on the computer. So you can work out what fraction 4096 bytes is of 128 gigabytes if you're good with your metric prefixes. But it's not very much, let me tell you. Anyway, I've declared 2 4,000 element arrays. I read one line into the first one, and then I have this loop here. Note the different loop. Yeah. fgets, if it's successful, returns a pointer that's not null. Yeah, don't worry too much about that. But that's the loop using fgets to repeatedly read lines. But I've got 2 problems. I want to say, is this array the same as the other array? And you can't do that. That's actually legal C, but does something quite different. You can't compare array contents with equals equals or less than or not equals. And you can't assign array contents. That won't, the C compiler will just stop and say you can't do that. So that's just broken. I'll compile it to show you. Call this snap line. We'd like to get snap line working, but the C compiler will say, Andrew, you can't do that. Alright, so let's fix my code. I'm gonna do it with a separate function. Compare line, I've called it. I'll call it compare array. So I'll have a separate array, and then I'll have one copy array. Right. So I'm going to do 2 functions, and then I'll have a working snap program to entertain me, working with lines of characters, not integers. I just need those 2 functions. Alright, what do we do? We need types. We need types, don't we? I reckon that's got to be return an int to say if they're the same. And I might actually simplify that. I might call that array1 and array2. And similarly here, it's got to copy the contents of the array, so it doesn't have to return anything. Its job is just to change the array. What do we call that? I'm going to call that one destination and that one source. There we go. What could go wrong with that? Let's fill these in. Let's look at how we'd code these up. Comparing 2 arrays. Alright, and copy arrays. What's the important thing for me to do now? The important thing for me to do now is really think about what these functions do, what their job is. And the best place to put that information is immediately before the function. I wish I could spell. So this one we want to return 1 if array1 and array2 have the same contents. Each element has the same value. There's more to be thought about there, isn't there? What does if with 2 F's mean? Hopefully you've seen that in maths. Maybe some of you haven't seen it in maths. I don't know. It's math lecturer talk for if and only if. Well, it's not just math lecturers. It's quite convenient. Any sort of reasoning. It's a term you use a lot in reasoning. So I'm saying this function returns 1 if, and only if, this is true. So by the way, I'm using a short... types. I haven't put types in. What are you thinking, Andrew? So yeah, what are the types? We'll just say char and char array and char array. And same here. Jeez. Alright, 2 char arrays. So there, I go back to here. You might be thinking, yeah, there must be smarter ways to do this. Yeah, particular editors will often have smarter ways to transfer prototypes and so on. Notice I haven't said anything about the length of the arrays. Yeah. Alright. These are char arrays, and we've read them in with fgets. What does fgets do? It puts a 0 in the char array to mark the finish of the string. So these char arrays contain what we call C strings. They're ASCII codes with a special value of 0 to finish them. So we don't have to worry about sizes, we just have to worry about finding zeros in the array. Let's do the copy one first. The copy one's easy. I equals 0. So we're copying from source array. So there's a loop that executes once. Oh, I can decide how I'm spelling that. I'll call it SRC. I'm using these abbreviations, this for destination and this for source, because we'll see them later in library definitions, the same abbreviations used, so I thought I'd bring them in early. Alright, now this looks pretty easy. The destination array I equals the source array I. Well, that's pretty nice. Oh, that's pretty similar to the code we want up here then too. Notice that function, its job is just to copy the arrays, returns nothing, so we don't need a return. Ooh. Now. Right. How about we go down array 1 and look at this. If they're not equal, we found it. Oh, poor coding, Andrew. Poor coding. If we find an element where they're not equal, any element where they're not the same, then we have to return 0. We only return 1 if every element is the same. And if we get to the end of the loop, we can return 1. I think that's pretty good. Let's there's one or two things worrying me there, but let's try compiling that. I think that's the right basics. There might be some issues at the ends of things. Let's try that. Hello, Andrew. Oh, look at that. So it is almost working. All right. I could spot a bug there, which is actually hard to trigger. How would I trigger it? Well, we might not be able to trigger it at all. Yeah, there's a tricky. There is a tricky bug here, which I'm not sure. There's a classic bug here that's not showing, and there's also an issue here. So I can probably trigger that bug. That bug first. Oh no, even with the new lines, yeah. The new lines in the... There are two tricky things here. Let me talk about them. So this is... The big thing I wanted to show you is here. A loop to copy the array elements and a loop to compare the array elements. Both functions have a bug, but it's sort of a second order thing. Let me show you the issue. The issue here is we don't copy the array element containing 0 to this array. So we should do one extra copy here. It can be that, or this will always be 0. So we need that extra statement there. Here we've got a separate issue. We get to the finish of array 1, and we've got there without founding any different elements to array 2. But what if array 2 is longer? So you really should do something like that. It's a bit subtle. You can think about that. Both those changes are really subtle things, and because of the way fgets work, they don't actually matter for fgets. That's also something you can try and figure out yourself. It's to do with new lines being in the array. All right, so that's quite nice. And that's the sort of bug you see with this sort of code. The issues with this sort of code where you're looking for that 0 marking the end of the array. Just handling that last condition there can be tricky. Now, there's a thing with coding where you should ask yourselves, if you've set a task, maybe it's an exam question where you're told you can't use any other code and you have to write it yourself from whiles and ifs and arrays, and then you've got no choice. But most coding we can use what we like. We have access to other things, And you might ask yourself, copying between char arrays, comparing these zero terminated char arrays. Shouldn't someone already have done this code? Shouldn't someone have written great code and other people checked it out and made sure it's 100% reliable? Should I be writing my own code for this and debugging it myself and perhaps having weird and subtle bugs that I don't know about? And the answer there is you probably shouldn't. I'm just going to take a copy of that because we're about to change that. Sorry, let me just make a backup here. There we go. There's a better way. Alright. And I didn't have to write any of this code. Let me junk that code. It's gone. Don't need the prototypes then. What do I need? What my friend here is that there's a set of C functions, a C library in string.h. If I include that, it defines the prototypes, the definitions for some very useful functions for operations on strings. One is string copy. Copy a zero terminated char array to another zero terminated char array. Ooh, and at this point, do I remember what order the parameters go? Oh well, wait, let me go to the manual entry and check. I think it has a nice manual entry. Oh, it's not too bad anyway. We haven't seen for loops. That's just like a while loop though. And there's the parameter order here. Yeah. String copy is nice because you can make sure it doesn't go outside the array you're copying to it. So I can tell it, oh, the array you're copying to is this big. Please don't go longer than that. That would be illegal. So there's string copy. Oh, except I'm putting it in the wrong place. I'm an idiot. Let's put it there to copy the array. That would be much smarter. Now, also in string copy.h is struct, which is a contraction of string compare, which you give it two arrays containing two char arrays, zero terminated, and it returns a value indicating where they are in dictionary order. So if we can actually, can we read the manual entry? We can try. Well, it's not too bad. Compares two strings s1 and s2, returns an integer less than, equal to, or greater than 0 if s1 is found to be respectively less than, to match, or be greater than s2 in dictionary order. Well, that's quite good. As manual entries, I've said, are not for people who've been written for people who've been programming for 6 weeks. So that's good as it goes. All right, it returns 0 if they're the same. So that's what we want there. So I think that's my improved function, just using string.h. There it goes. I just want string.h on the screen. Save it. Have I got it right? Let's find out. Does it handle something that's shorter? Longer? Alright, let's see if we can get a snap out of it. There we go. Alright, so that's my snap program. Overcoming these issues here. So with integers, look, I can use equals equals to see, do these integer variables have the same content? I can use assign to say, take the contents of this int variable, put it in that. Arrays don't support either of those operations, but if I go to these C library functions, I can say copy this char array to this char array, this char array, better have a 0 somewhere in there to mention it. But if I want to be safe, I can say never copy more than that many characters. That's how big this array is. And struct comp we saw to see, do these char arrays have the same value in? Consequence is that gives me this. Yay! I've implemented one of my favorite games using string.h. Now you might be saying, what other useful functions are in string.h? What else do I need to know about? Alright, I've got some that you might, let me repeat, don't rush out and get this tattooed. You will always have access to this information. We don't set exams expecting you to remember 27 functions. So perhaps most useful of all the string.h functions is strulen, short for strulength, which goes to the char array, goes through the elements and stops when it gets to the 0, so it tells you how long the string is, counts the number of characters before it gets to a 0. Of course, if it doesn't get to a 0, that will produce before the end of the array, that will give you a runtime error, or worse. Struct comp we just saw. Struct copy, it's always better if you can to use this version that's got the safe limit there. Similarly, if you want to append strings, there's struncat. Sorry, cats don't have anything to do with the cute fluffy things. It's actually short for concatenate. So it's string concatenate. Why isn't it called string append? Excellent question, but it's used to append strings. You might, alright, so which ones will you'll definitely use this one. You'll definitely use this one. You'll definitely use this one. Oh, well, you'll use one of the copy ones. You might use a struncat maybe. And you might use these last ones, which search either backwards or forwards through a string for a character, maybe. Is that it? No, there's actually more useful functions, but these are enough for me to highlight for today, I think. So there is a pile of useful functions there. Alright, in string.h, but none that I think you'd be very likely to use in this course. You might be saying, oh look, I think I could code up strulen. Yeah, you could. You could code up all of these functions. There's nothing particularly magical about these functions. They can all be coded up in a page or less of code. In fact, I think we saw the manual entry even. See, this is a manual entry after my own heart. The person writing the manual entry saying, how do I explain... Oh, sorry, I've got to get there. How do I explain... No, it wasn't struct comp, it was struct cat, wasn't it? Struct copy. They're asking how do I explain struct copy? They say, oh, I put some C code there. Alright, I'm not going to talk about for loops. You can look up for loops yourself. It's very similar to a while loop. If we've got time, maybe next Thursday I'll briefly mention for loops, but they're not a big thing, tiny thing. Alright. I think that's all I wanted to say about string.h today. I want to move on to talking about them in structs. I'm going to ask Alvin. I haven't been able to keep up with the chat. Alvin, is there something in the chat?
I think Liang provided us with a good solution, but this may be a while ago, which is when you increase I before array I not equals to array to I works as well. So I'm not sure if that's somewhere beforehand. So
I can get it back. So I've saved this. So sorry, I'm not sure what the question was though. No, I did. But there's a little bit of weird code here and there, which I'd suggest you work through if that's worrying you, and think about it. both of those examples are already on the class website. Oh, and we've got Shrey today. A big shout out to Shrey, who's back in the chat today, but had a huge couple of days with assignment 1 coming in, sort of organising the course forum. So say hello to Shrey in the course forum. All right. Let me switch topics then. Yeah, I know I could happily go in programs like this. I could talk about programs like this for hours and hours and hours. There's all sorts of interesting sort of side things and all sorts of programming things you can illuminate with this. But we have to keep moving because we've got to get in a position to cover some crucial topics, which you're working with in week lab exercises. So I've got to get there to get you ready for that. All right. Structures. A compound type. A way of creating a new sort of class, if you like, of variables. And they let us put different types together. Arrays are always arrays of the one type. It's very boring. Array of int, array of double, maybe an array of arrays. Structs, you can have 2 ints and a char together, or you can have 2 arrays and an int together in a struct. So they create interesting possibilities for us. And so struct is a C term. It's what C calls them. It's short for structure. The even older term would be to call it a record. But every language has something like this, and in every language they get slightly different naming. Now, there's an example of a struct. And what do we see there? This is our setting out beforehand the layout of a struct. Yeah, we haven't had this before. It's a 2-part story. So let me switch to code here maybe. Let's me open. Have I got a... It's a 2-part story with structs. Yeah, this works pretty well. So first I have to put out the template, if you like, of the struct. This doesn't create any variables. This just says what struct benders are going to look like. So I say a struct bender has 3 sub-variables made up of 3 variables: name, element, and power, and these are their types. Power is an int, that's easy, and a little more tricky is name and element are arrays. Yes, you can have structs containing arrays, arrays containing structs, structs containing structs, structs containing arrays of structs. You can mix and match to your heart's content. And you can have pointers, which we'll see shortly. Now, here is the template. All right, let me show you then creating a variable. The second part, so it's a 2-part thing. I've set out this template for C, so I can say I want a variable that's a struct bender, and what do we call it? I'm trying to follow the example code. Let me look at what my example. All right, so we've called it avatar. There we go. Come on, VLab. There we go. And gee, please don't put silly messages on my screen. Let me throw away gee, silly message. All right. Let's see if, yeah, compile early, compile often. Please gedit. No. All right, let's try DCC simple bender .c. What does DC? DC says, well, Andrew, you created this variable avatar, but you never do anything with it. Are you sure you know what you're doing? All right, no, don't really. All right, so that's created a variable avatar, and that variable avatar's got all of these parts. How many bytes for that variable avatar? Oh, we never, yeah, we could actually look if we want. We saw that size of before. What was the trick? Just recapping. Remember, size of tells us how many bytes to hold something. So I can say how many bytes to hold a struct bender, and print that out. Let's put it turn 0 here while I'm here. Make my main look lovely. Alright. That's nice. Let's compile. And run it. Oh, 204 bytes. There we go. Yeah, it sort of makes sense, doesn't it? If we imagine a char's 1 byte, that's 100 for that one, 100 for that one, and just 4 for that one. The stories can get much more complicated, but that sort of makes some sort of sense to us, doesn't it? Why do we need size of again? It's for memory allocation. You're saying, can we do memory allocation with structs? Yes, we can, but not just yet. Let's try and do something simpler with a struct. Yeah, William's asking in the chat, so structs are like templates. Yeah, they're very much like a template. Yeah, template's a good word for them. Alright, I've created this variable. I want to talk about a sub part of it. There's a new operator, dot. So I can use it to talk about a sub part. So I want to talk about the avatar's power. I can say the avatar's power is 85, like that. I can use it anywhere I can use an int variable. So anywhere I can put an int variable, I can put an avatar power. So that's all valid C. Actually, bear with me for a second. Maybe I can figure out how to stop that stupid message. Talk among yourselves. Well, you can't really do that, can you? Because you're all in separate places. Or you better be under lockdown rules unless you're members of the one household. And we certainly support keeping to the lockdown rules. I'm actually in another window you can't see, SSHing into CSE, trying to find out what's happening in that directory that's causing gedit to print stupid messages. And that's left me none the wiser. Alright, we're just going to deal with gedit sort of dumping on our terminal. Why do I always forget df? There we go. So dot. Yeah, dot. What's on the left hand side of the dot? Must be a struct. Must be a variable. Must be a variable that's a struct. What's on the right hand side? Must be a name. Which name? And this for this depends on the struct, but for this one we've got 3 choices. The name could be name, sorry about that. The name could be element, or the name could be power. So it must be one of those things to talk about a sub part of the struct. If this is itself as a struct, can you put a dot there? Yes, you can. You could have, a.b.c.e if you nested structs within structs within structs, and sometimes that happens. So how do I get a name into the struct then? Like this, using stru copy. Away we go. I think I'll use string copy, I'll be good. Max length. And I could do the same again to put in my power. What's my power? My power is coding. There we go. Sorry, my element. That's what I want. Element. How do I print out those fields? Well, they're char arrays with zeros on the end of it. Printf%s handles those, doesn't it? So we can get that with, oh, not what I wanted at all. So name equals %s. Name. Now if I'm smart here, I print out the element similarly, but if I'm smart, I compile now and see if this works before copying the code. Before you sort of, yeah, if you compile early, test early, discover bugs early. Struct.element. What were you thinking, Andrew? Even gedit's highlighting it as in, to say that's not smart. There we go. Oh, and I've forgotten to include string.h. What was I thinking? Getting there. Does it work? Alright, so I can finish off my little example of putting values in a struct like this by putting my element out. Makes more sense to put. Ooh. Uh-oh. Okay. So in a tiny program, absolutely tiny program, we've used a struct, created a variable of that type, put some values in its field, and then access those fields to write it out. So this is using the dot operator, dot operator, dot operator, dot operator, dot operator. So that's good. Someone in the chat is asking, did Andrew make this example? No, I didn't. I am responsible. Thank you to the person who liked my music choices, musical lyric choices for the lab this week. I was responsible for those, but no, this example is due to Mark Chi, who lectured this course in the last few terms and will lecture it again, I think, in T1 next year. So he's responsible for this choice. The Last Airbender really wasn't something I was huge into. Alright. Someone's asking, is this like classes and objects? Yeah, that's Java talk, isn't it? Yes. So this has a lot. This is sort of like a ancestor, ancestor. If you, a few of you will have seen Java and classes and objects, and this is sort of an ancestor to that, which you'll get if you make it to COMP1511. You'll get to explore that. All right. Now pointers. What about pointers to structs? There's something about pointers to structs. Let me show you. I've created that struct. I could also have a variable that points at that struct. So we could have a struct bender star. What do we call a variable? Call it many things. I'll call it SP for just because we're testing out struct. It's not a great name, is it? Oh, actually, no. Well, I'll call it Andrew. There we go. That's a pointer, and I'm going to make it point at that at that struct we've created. What have I done there? Yeah, consider what I've done there. First, I created this struct. That'll be we peaked, and that's 200-ish bytes that can hold name, element, and power. Then I've created another variable called Andrew, which can point at a struct bender. So it actually contains a memory address. If I peek, it'll probably be 8 bytes, I'd guess. But it can lead me to a struct avatar. It refers, sorry, to a struct bender. It can, and I've made it refer to avatar. So Andrew contains, I said, make Andrew refer to avatar. That says get the address of avatar, really. Can I do everything down here just with this pointer? Yes, a pointer to a struct is absolutely as good as gives you full access to everything in the struct. Anything you can do with a struct, you can do with a struct you've got a pointer to. All right, there's one caveat. There's a nasty precedence issue. And yeah, precedence is what your grade 6 maths teacher talked to you about or something. Plus and minus, times and divide. When you got complicated arithmetic, what does it all mean? We still have the same problem. We have to put brackets here, but if we want to use the pointer Andrew and then access the power field, we can do it like this. So that says whatever, get the struct that Andrew points to and set its power field to 85. Now I'm going to stop there and compile to make sure all of that works and I'm not lying to you. I'm going to save my file, then I'm going to compile it. Ding. Look at that. Alright, so using the pointer, saying why you do that, you're making life harder for yourself. It's a first step. These little programs are exploring different ways of doing things which we can then use to do better things, much more powerful things. So we'll explore them in little programs while we can see them in miniature, and then we'll use them in bigger contexts. So we're just trying these out in a sort of little sandpitty way, explore these, see what it does, and then go on. Alright, oh yeah. Right, so this syntax is a nightmare. It's ugly, it's hard to understand, it's error prone. By the way, this means a different thing. If you leave out the brackets, what that means is the dot wins, and it's the brackets are there, which doesn't make any sense because Andrew.power is not a pointer, it's an int. So if I leave that, I'll show you. I'll compile, and I'm betting DCC will give me a line compile error for line 16 saying, oh, yeah, oh, look at that quality error message there. That is impressive. In the past, C compilers would not be nearly that helpful, but that's really trying to help you out there. Let me explain what that error message is trying to say. It's trying to say there's a better way. If you've got a pointer to a struct and you want to deal with a field of the struct, there's a better alternative to dot and asterisk. Yeah, sure, we've seen dot get a field of a struct. We've seen asterisk to reference a pointer. So they're the tools we've seen, but there's a better way, but puts them all together in a more convenient form. It's just convenience. You don't like this operator, you don't have to use it, but your programs are going to be ugly, error prone, and hard to read. So there's a nice little shorthand. A lot of people call this stab, which I don't like. So some people call it the stab operator. I think I call it the arrow operator, but it's up to you, I guess, what you call it. Sadly, our exam won't have questions like what is the name of this operator. No, it won't have easy questions like that. you've posed in the wrong course. Our exam has questions like write code to do blah, and you may need to use this operator to do them. Alright, and I can just use this. I can change my program everywhere I used avatar dot. I can now use, because Andrew's a pointer, I can just I guess I could get smarter about this, couldn't I? And the last one. There we go. Alright, I think that's all correct. Let me see, make sure I'm telling the truth when it compiles. That's lovely, and that's now the same program. Alright. Now what's the big difference between dot and arrow? Right hand side is just the same. Right hand side of dot is a name from the struct. Right hand side of arrow or stab is a name from the struct. It's the left hand side that's different. So for dot, the left hand side must be a struct. For arrow, the left hand side must be pointer to struct. So that's the big difference. Otherwise, there's that big crucial difference, but apart from that, they're almost identical. They are identical.
Sorry, Andrew. So I think Shay brought up a really good point there. The type that we are talking about currently is either a pointer to a struct bender or struct bender in general. I guess some people are confused seeing struct as its type, even though the actual type is struct bender.
And I'm not at all surprised. This is tough. So what's the type? The type is struct bender. What's the type? Struct bender star. So those are the types of two variables. So this program now has two variables. Variable 1 name is avatar. Variable 2 name is Andrew. Variable 1 is a struct bender. Variable 2 is a struct bender star. So yeah, it's got a lot harder, hasn't it? Before it was really simple. Our types were int, our int types were double, our types. Now we've got these custom types. So I've done this custom type, a struct bender. It makes it harder to read because I'm introducing words that are part of types. Previously, all the type words were int, double, which were predefined by C. But now I can have struct anything, and I should be careful about what anything, what I use there to try and avoid confusion. Sometimes programmers have special rules for the way they do struct names to make it a bit easier to understand. Alright, so now it's a bit of a recap, but asterisks, what did the asterisks, let's take, if I've got a pointer, there are two operations with pointers, aren't there? There's ampersand to say give me the pointer to something, give me the address of something, and that's what I'm doing here. I'm saying give me the address of this variable here, and then I'm putting it in this variable here. What's the reverse? What's the how do you go backwards from that? Invert it if you like. It's asterisk. So asterisk says given a pointer, talk about the variable it points to. Print it out, change it, whatever. If you've got a pointer to something, you can do what you like. So using asterisks, that's called dereferencing. This is called, the ampersand is called referencing, and the asterisk is called dereferencing. And my first version of this, I said dereference the pointer with an asterisk, and then talk about the power field. So that's a bit nicer, and it's putting the fields together. So that's saying refer to whatever Andrew points to, and that better be a struct because we're using a dot operator. And yeah, we have a new power. We create new types separately. So this doesn't create any variables. Lines 5 to 9 don't create any variables. They create a new type, is what I'd say, for a variable. But William in the chat said, well, is that sort of like a template, isn't it? Yes, it is. It's a new template. But the computer science word for template in this context is really type, I think. So, and then arrow then is in shorthand, another way of writing it. So I'll make lines 16 and 17 exactly the same. So those two lines are now, except for the spelling mistake, identical. They do exactly the same thing. So arrow is a nicer way of writing asterisk the pointer and then dot the pointer to this field. Instead of writing brackets, asterisk, Andrew, close brackets, dot, power, I can write Andrew, arrow, power. But the same. You want a nice phrase to learn. People who work on programming languages would call that syntactic sugar. It doesn't add any meaning to the language, any extra operations to the language. It just makes it prettier, and they think that's just unimportant. But to you, the coder, these changes can make life so much easier. It doesn't let you do anything more, but it just lets you write simpler, more readable programs, less risk of errors. All right. We've just passed the hour, which is quite convenient because I need to take a short break from talking. So I'm going to take a 5-minute break from talking. I'm going to come back and talk about structs and memory allocation, and then do a more complicated example. So get up, stand up, maybe even walk outside, admire the beautiful day in a COVID-safe way, and back in 5 minutes. All right, we're back. Yeah, there were lots of questions in the chat, and these are hard things to get your head around. There's one good advice was, go away, think about these things, and then maybe ask a question in the course forum, and Shrey or one of the other people who work in the course forum can try and give you a detailed answer. All right. What I wanted to try doing was, rather than use a struct that we declare, use malloc to allocate the memory for the struct. So this, let's remind ourselves what that did. Oops. Let me get. So this creates a variable called avatar of, what was it, 202 bytes. So I can also get 202 bytes using malloc. If I know what I'm doing, I can say malloc 202. Please don't do this. But oh, in fact, I could do it down here, couldn't I? I could say, I could put that. I have to put it somewhere. Yeah. If you talk to people who are research education, they say never do this. Never show your students bad things. No, they won't get the message that it's bad. So we're living dangerously here. All right, that says set aside 202 bytes. It returns a pointer to it, and we'll make Andrew point to that. All right. How do I know that's enough space for a struct bender? Well, I don't, and it's just never do this. You always, when you're using malloc, you should be using size of to say how big is something, so that in every malloc call you do in this course, pretty much every malloc call you do, you should have a size of there to say, how many bytes do I need? So I can say, tell me how many bytes are needed for a struct bender, and we peaked and saw that was 202. Give me that much memory. Well, let's try that. Let's see if that compiles. I think I'm probably missing a hash include. Yeah, I'm missing. Malloc needs a hash include for stdlib.h. Why, you might say? Yeah, it seems just some of these things seem just designed to make student life harder. All right. There we go. Compiles. We tried running it, but it's going to work. And actually, a lot of programming with structs involves not having a variable of type struct, but instead using malloc to allocate the space for the struct and getting back a pointer and keeping that pointer somewhere. And that's what we're going to be doing mostly from now on. Alright. So most of our coding is going to look more like this. There it is. Yeah, that's quite a nice example of a combination of malloc and a struct. There's one thing I'm not doing here, and we're skipping over in this course. What happens if the malloc doesn't work? That is possible. It's not very likely, in fact, but we'll come back to that. That's just, we've got enough things to worry about at the moment. Beautiful. All right, let's look to a more complicated setup. Let's look to a more elaborate setup. I have some predefined types here, I believe. Structures. What sort of comment is that? The sort of comment I hate. Yeah, there we go. So what have I got here? Well, this one already seen. So I want to be able to represent a team of benders. A team containing up to 4 benders. How do I do that? I've got going with a second struct definition. Struct team Each team has a name, which we'll use max length again. So the team's got a separate name. Players have names. The team also has a separate name. It has a team size, how many members the team has, and it has an array of pointers. Oh wow, look at that type. That's a little scary. So it's an array of team size, or an array of 4 things. That's easy. But look at that type. The type is struct bender star. So each element of that array is a pointer to one of these. It's pretty amazing. Alright, so we've got one of these, and it's got an array in it of 4 things, and each one of those leads to something of this. Alright, let's look at how we might want to create a team. Alright, so we might have the A team. Alright, we'll have the A team. The A team. So struct team star, A team is the variable, struct team star is the pointer, and we'll allocate some space, and we'll say give me enough space for a struct team. Right, at this point I'm going to compile. I'm getting a bit nervous here. Let's see if all the stuff I've written makes sense in C. My recollection is if things are going well, it'll just complain you haven't done anything with your A team variable, Andrew. There we go. Unused variable A team. Everything else looks good. Yeah, I'm sorry about the Slack noises. I should quiet my Slack notifications. Next lecture for sure. It's like hearing the doorbell on TV, isn't it? And then you go to and then you start going to answer your deal. All right. I've got to give my team a name, of course. The A team. We'll call ourselves the best. Yeah. And a team. Alright, how do we put someone in the team? Oh, now it gets fun, wasn't it? We want to create a team member. So it's a team. And then team member. Actually, I don't like team. Do I like? Oh, I'll leave it as team members. Members might have been a better name. I'm not sure. So that's our first team member. Look at 2 arrows in a row. Can that really be right? Oh no, I can't. It's the A underscore team. There we go. A underscore team is pointed to a struct team, has a field team members, which is an array, and index 0 is our first team member. And we'll use malloc to allocate space for that, and size of struct bender. We have a team of benders. Are we doing this in the best possible way? Yeah, interesting. Maybe not. And then we can fill this in. Whoa, it's getting even more complicated. It's sort of nice to see this though. So what's the power of this team member? Their power is 17. actually. I'm breaking my cardinal rule, aren't I? Let's compile and make sure that's all still making sense. Oh, and it's not. It's saying to me, look, this is not making any sense, Andrew. That dot looks okay, doesn't it? But you've got to think really carefully about types. What type is this whole thing here? What type is team members? It's a struct bender star. What goes on the left of us? In other words, it's a pointer to struct. A pointer to struct bender. What goes on the left of a dot? A struct. What goes on the left of an arrow? A pointer to a struct. So I can reason it out. It's pretty common. DCC's coming to the party there and even saying, oh look, that looks like it should be an arrow. Alright, let's clear that. This time for sure. Ah, alright. I've got I've got 2 arrows in a row and I've managed to use it. So now we have to fill in name and element. Alright, so we'll make this bender Alvin, and if I can do my same thing again. Are all the types good there in DCC? Yes, they are. Then I'll just copy that line and say an element. Do you have an element, Alvin?
Maybe fire.
Okay, Alvin's element is fire. There we go. Alright. It's not doing anything much, is it? Alright. Oh, we've got one more thing. We've got to set our team size. Yeah. That's the last variable. That's the last field here we have to see. We're creating a feed. It's a somewhat lonely team at the moment. It's only got 1 member. But that'll let us actually... It's not actually bad to try and debug things with just very small cases. So a team of 1 member is probably pretty good to try and debug some of the other things we want to write. So the size of the A team is just 1 at the moment. There we go. Alright. Now, we've created a team. What can we do with it? Oh. See, it's so easy to accidentally make mistakes. Team size. All correct C now. Now, what's really common when you're doing this sort of stuff is the first code you write when you create a new struct is code to print the struct, to allow you to output the struct, because even if you never want to output the struct, how are you going to debug if you can't see the contents of a struct? So it's almost always when you do a struct you create an output routine. So let's start off with void printer bender, which takes a pointer to a bender and prints it. So struct bender star B, I guess, I don't know. We've already got code for that in the mucking about with. We probably should. You probably should debug it separately over here, but we won't. Copy it into place. So close. this time for sure. Alright, that's actually a nice little function. Yeah, that's worth looking at and thinking about. Yeah, look at that. So there, oh, one more thing I've got to do. I've got to copy the prototype. And of course I've tested out as well. So let's copy this up here. Put a print the bender. So I'm going to have that. And let's try it out. Let's print out. Now we want something that prints a team really, but we'll try it out. Let's see if we can print out Alvin. For this, with his power of 17 and his element of fire. Right, have I got it right? Fingers crossed. Ah. Right, so there's a print bender function. Now we want a print team function. How are we going to do that? Well, it's going to take a struct team star. You might be saying, Andrew, can you write a C function that if it's given a bender struct, prints it, but also could be given a team struct and handle it? No, C doesn't have that capability. For each type, you pretty much need a separate function. There are, you come back in some of our third year courses and you can see languages and ways of doing this and clever ways of doing this across programming languages. But generally for C, you need a separate print function for every type. So if you have 5 different structs, you know, struct A, struct B, struct C, struct D, struct E, you'll have 5 different print functions, which can get a bit tedious. But let's have a look at this. So we want something that prints a team. And I've called the argument T. Yeah, that would make better. Print the team T refers to. Print the bender B refers to. That'll actually work. Teams have a name field just like benders by some weird thing. Now we need to go through each team member and print them out. How would we do this? How? Well, I less than team's size. You know what's annoying me? This should be team name. I hate inconsistency. You'll see this a lot in coders. It's team size, team members. Why isn't it team name? I'm going to fix that. It's just annoying me. There we go. You're saying, why would that annoy you? What's in a name? I'll tell you, a hell of a lot's in a name. Getting names right is so important. It doesn't change how the code works, but it changes how the code reads. That's better. Even better. All right. And we can say this is team member %D. Right. So Alvin is team member 0. Put a colon there. And then I can just call print bender to print the team. Print bender T team members I. And I'm hoping I've put together a lovely bit of code here. Fingers crossed. Fingers. No compile errors, no compile errors. Oh, so many compile errors. There must be a million things wrong with my program. There may only be one character wrong with my program. We'll find out. Alright, that semicolon there doesn't matter. Now you could go and look at all of these other errors, so you could look at all of these. It's possible none of those are real. It's possible that semicolon just confused everything. The compiler went off and couldn't work out what was happening and got completely lost. So honestly, it's worth then just recompiling. Sadly, there were other errors. Which I can't see. Come on. Conflicting types for print team. Oh, I put it prints a struct team. What was I thinking? Save the file. Oh. Oh, I have to call print team now. Now I'm good. I can say print team and print out the entire A team, which just consists of Alvin. But I recompile. Yeah, there we go. Team name is the best. Team member 0 is Alvin, and he's the only team member. But we can add a team member. Now looking at my code, Alvin, you have a question.
Yes. So I think Shay brought up a good point. So I think his question is, why do we need to use malloc for struct team star A team to get memory, but not something like int A?
When you get memory in C, you have to know what type you're getting memory for effectively. So I wanted to hold an object of type struct team, so I have to allocate enough bytes for that. So I say size of this, and then to use it, I have to use a pointer of the appropriate type. So I say I'm going to be dealing with a struct. I want to do things with a struct team. Here's the template. Here's what it looks like. And C will look at it like that and go, ah, that's 227 bytes. And I'll put them in. And C will figure out some internal things about how it stores things in memory, where it puts the team name, where it puts the team size, how it lays out the array of team members. This gives me the bytes. Now you might be saying, couldn't you do this easier just by declaring a variable of that type? Yes, you could. You could do things just to cover this simple example, could be done in a simple way. But this is taking our first steps to be able to write incredibly complicated and powerful code. So if you just wanted to represent a team member, just Alvin as a team member of 1, there are simpler ways. But this is using powerful techniques in demonstrating them. And here is the pointer type. We're saying make this pointer can point at a struct team, and malloc says give me enough space to hold a struct team. Together, now I'm right. That lets me do what I want. And I'm repeating this for a struct bender here, and we might look shortly at pushing that off to a separate function actually. But first there's an issue here, and the issue is a hard one. The issue is the program has a memory leak. For every malloc there should be a corresponding free. So every piece of space you allocate with malloc, you should free up. You say, well, how can I check? Well, DCC is your friend here. DCC will actually has a special option. I can say -- leak - check, and I run the program, and it will tell me if every piece of space I allocated with malloc was freed, and if not, it will give me some indication. It's saying, look, Andrew, here you allocated space on line 29, but you never freed that up. It's not the only place, but it's just telling me one. Memory leaks are hard things, but we want to take our first steps. So we want to start off the way we want to continue as a coder, writing code that frees up the memory. So malloc is really powerful, but so is a chainsaw. You've got to use it with care and with discipline. The best thing though here is to write a function. And this is another classic function, is to write a function to deallocate a struct. So you might write, we haven't written the function to allocate a struct. We haven't done the allocation code as a separate function. We could, and will if we've got time, but allocate a struct, deallocate a struct, print the struct. They're the sort of classic programming things you do when you think of a new struct. So free up the space. How do we do that? All right. Well, let's grab that one as our starting point. Free team. Yeah, it's the and the function to free up space is this. Free t. There we go. Looks nice. Change the name. Put it up there. That's good. Just have to push that prototype up. Put it there, I guess. With a semicolon. See, we can compile. Oh, wait a minute, it didn't recompile. But what I really want to do is recompile with the leak check. Have we fixed the memory leak? It's giving me a different line though, isn't it? Oh, yeah, it's saying, oh look, you haven't freed the memory you allocated there. Now we've got a complicated situation, haven't we? So we've got a struct team, but it contains an array of pointers to struct bender, and they got allocated with malloc as well. There's only one of them, Alvin, but we allocated him here. So we've got to go through the team members and free up the memory we allocated to represent them. So we've got to do a free for each team member as well. No, it's not that hard. The concepts, yeah, this is one. The concepts here are really hard. The coding, once you understand the concepts, the coding is often just a few lines. But knowing what few lines to write, oh, it's so hard. So for each team member, and we've got the team size field, so that's a loop that will execute once for each team member. Oh, we've already got the loop down here. Should have used it. Should have used it already. What was I thinking? Free team member I. So go through the team, freeing each team member. Try that up. So close. Team members. Sure to work this time. Look at that. No memory leak. So we allocate some space, we deallocate some space. Everything is in balance. Alright, so it's a pretty simple example, but it's just walking, allocating a struct and then putting in it a pointer to another struct which we allocate with malloc. We've got it halfway to what we're going to work on in next week's labs. Fortunately, we've got next Tuesday's lecture to get us all the way. So now. What else did I want to look at this? Oh, I wanted to show you something. You'll probably make this mistake anyway, but everyone does. But you can't do this. So here I've said free the team and then free the team members, and I'm hoping, is DCC smart enough to pick this up? That's a nasty bug, but it's also hard to pick up. I'll try DCC and see if it can pick that up at runtime. Oh, it can. Access to memory that has always been free. Thank you, DCC. That's not an easy thing to pick up. So what am I doing here? I'm saying here, look, I'm done with the struct team that T refers to. But then I look at it, I say, oh, but then you say, look at the team size field of the struct team that T refers to. But I've already said I'm done with it. So this is a huge error. This is a big use after free is the most common way to call it. Use after free. It's one of the biggest sources of bad bugs. These are some of the worst bugs you can imagine. These also create some of the worst security holes you can imagine. Freeing up something and then using the pointer, saying to malloc, oh look, I'm done with the space that this points to, but then actually looking at the space. What's so bad? Something else can start using that space is the issue. That can't happen in the tiny programs we write, but in real programs it's a major possibility. In real programs it's a big problem. So that's why we don't want you. We want to spot this straight away and point out to you. No, don't write code like that. We want to start you writing off code that doesn't have this problem. So that's why we've got DCC, which goes to some lengths to discover this. It's not so easy to discover that and tell you, no, you've done this. Don't do that. It's bad. You have to. So it's a classic sort of thing. If I've got a complicated structure, is to do some things associated with being finished with that structure. Then, as a last thing, say I'm done with the structure itself. All right. Don't worry too much about that. If that seemed scary and overcomplicated, well, all of this is scary and complicated, but that's even more scary and complicated. I don't like this. This is just messy. I wouldn't mind putting someone else on Alvin's team, but it's just messy there. I'd like to put all of this in a separate function. How would I do that? I want to create bender function. That's what I want. See, I missed that one. Oh, I really want that bit of it as well, don't I? I want to put all of this code off in a separate function. This is just too messy, too hard to read, too confusing, and plus I want to do this multiple times. It was already a mess just to allocate, just to create Alvin. A create bender function. Right, a create bender function will return a pointer to a struct bender. Yeah. What does it need? It needs to give me their name, their power, and oh no, their name, their element, and their power. What am I thinking? Oh, all right. So I'll call malloc. Let's say what do we call it? In. We'll call it in. Why not? Set that power to whatever's passed to me as the third argument. Set their name to whatever's passed to me as the first argument, and set their element to this. I think I've got this. I think I've got this. Now something's worrying me here about clashes of, I'd say, namespaces is what I'd say. But the question is, can I have a struct field name the same as a variable? And the answer is you can. If it worries you, you don't have to, but it's sort of something you do pretty naturally as coding. I prefer to initialize these in the other order. It doesn't matter at all, but come on. That would be better. And the last thing we'll do is return that pointer. Now if I've got this right, up here I can now say equals create a bender.
I think you may want to change the element to be an array.
Oh, I think you're right. All right. Let's increase, as he did that, we'll increase Alvin's power to 20. There we go. We've got a create bender function. Takes a name, element, and power and gives me back a whole struct bender, which it's allocated with malloc. I'll put a comment here. That's sort of a classic comment saying, are you giving, if you're giving the caller back something you've allocated with malloc, telling them they must remember to free it. So that if they call you, you're giving them a pointer, but it's their responsibility to free it. I think if I put a prototype for this up the top, and I haven't stuffed up anything, we've now got have I stuffed up anything? Oh, will it create a team with Alvin in it? I'm hoping so. Alright, so we can put someone else on the team. Well, let's put Shrey on the team. Alvin, we don't have Shrey on audio, so you'll have to guess a power for Shrey.
21.
Oh, element's what I meant, but yeah, all right. We'll make you. Well, that's generous of you. We're making Shrey more powerful. What's Shrey's element? Though, is what I want to know.
I think Earth is one of the elements, I believe.
Oh, all right, we're going with Earth for Shrey. I think there's more than 4 elements in the last Airbender, but all right. So we've made Shrey power 21 Earth. Oh, we've put him in array element 1, and we should have a team of 2 now. Okay. Okay. Let's see if I can compile. I can. So we've got a team member of 2. I've got a create bender function. I've got a print bender function. I've got a print team function and a free team function. I could even put all of this code off in a separate create team function, couldn't I? I'm going to do that just because I'm that sort of person. So I'm creating a team. This function sort of less useful because everything's embedded into this. It's sort of hard coded. You sometimes create functions like this more for testing than anything else. So, but it's nice to see the form of the function anyway, the type of the function, and what will the type of the function will be. It will be a struct team star will be the function. We'll call it create team. It'll take no inputs, so we put the weird word void there to say I'm not giving you any inputs, and I've got that wrong. And up here now I can say struct team net equals create team. I can have a beautiful main that says create team, print team, free team. And your main function should be things like that. It should be quite powerful. Just a few calls to powerful functions. If I've got this right, I can then put this up here. What have I done? That's right. All right. Almost there. Almost there. Have I got it right? I have. Look at this. All right. So this has made a nice main, and the create bender functions is sort of super useful because in create you supply the 3 fields and it gives you a new bender. So that's a classic function. This one's sort of a special hard-coded function. You could write an input function, but that would actually go for pages of code that read in Alvin and fire and 20 and something like that and ask for the team size. So you could write something here that's more complicated using scanf and fgets, but we're not going to do that. But that's quite nice. And that's beautiful. Yeah. And this is... So, yeah, it all makes sense. We've got a team name, a team size, and then pointers to our benders in our team. So we've got an array of pointers to struct bender, and each of these structs describes the bender with their name, their element, and their power. That's quite something. Alright, we're almost out of time together. I wanted to highlight, oh no, yeah, don't worry too much about this freeing, but just remember for every malloc there should be a free, and we'll work with you to get that going. But the malloc is the important thing, understanding a function like this that says, look, give me a struct bender, give me back a pointer to a new struct bender, and it does it by saying to malloc, give me the memory necessary to hold a struct bender, put it in this variable n, which is a pointer to a struct bender, then I complete the fields. I complete the power field, I complete the element field, I complete the name field. And because name or element, these zero terminated char arrays, we have to go to a stru copy to actually copy into that. But that fills out the struct. That's quite pretty. Alright. I wanted to, in our last minutes together, just to foreshadow what's coming in Tuesday's lecture. That's all those string functions we saw. You can browse through those or play with those if you like. Not a bad thing to actually explore some of those. I think in next week's lab exercise we actually get you to do a little bit with get a command line. I think the first lab exercise is command line arguments, and maybe you might want to use some of these functions, I think, with the command line arguments. Justin's asking a good question. Thank you, Justin. Why don't we use stru copy for power? Well, you can't tell looking here, can you? Yeah, it doesn't make a lot of sense. How can I tell? I have to know what's in what a struct bender is, and then what type this is. And if I scroll back, so yeah, it's crucial to know that, isn't it? I look up here. Now Justin, you can tell, can't you? Two arrays, so I use stru copy for copying the char arrays, but what type is a power? It's an int, so I can just assign it. Yeah, thanks for that question. And you'll do that a lot. You'll be looking down at this code and saying, oh, what's that struct look like? And go back to it. There's a reason. So I'm working with, I have 5 monitors here strictly. I only really use 3 of them much, but I have some stuff on other monitors. And there's a reason programs like multiple monitors, they'll have a pile of struct definitions open on one monitor, documentation open on another monitor, and actually be coding in front of them perhaps. So yeah, you work on small, in this course you work on much smaller programs, so it doesn't quite get that excessive, but you'll still get used to having at least 2 windows open side by side. Alright, I was just going to foreshadow coming next week, yes, it is coming next week, is structs that look like this. So what we're going to deal with in Tuesday's lecture is a struct. This one's called a struct node, and it contains a pointer to the same to a struct of the same type. So which is a little weird. We can have other fields, but these pointers let us do amazing things. That means we can have a struct node, and it can have a reference to another struct node. So next Tuesday's lecture is all about this, and after the first, I think at lab exercise, it is next week. After we'll get you actually playing with this. So we'll dive into this. We'll go all through this in Tuesday's lecture, and then you'll work it in the lab exercises. And that will be the lab exercises not only for week 8 but also for week 9, I think, because yeah, that's what it's going to be our big topic for the coming days. All right, everyone. Thank you, Shrey, in the chat. Thank you, everyone else in the chat, for all the questions there. Thank you, Alvin, for your help today. So I'll talk to you all again on next Tuesday. So see you then.